Now let us talk about work. Now we have come across this idea of work before. It was in the equation for power, that power was equal to work done divided by time. Now we do work whenever we transfer energy. So whenever the value of energy in one energy store goes down and the value of the energy in another energy store goes up because there has been an energy transfer, then we say work has been done. I suppose it all depends on whether or not we're talking about a closed or an open system. You see, if you remember, in a closed system, there was no external forces acting on the objects in question. And so there could be a direct transferal of energy from one store to another store, and all of that energy would be accounted for. In contrast, an open system would behave slightly differently. That what you could do is you could have a force from the outside world acting on your object that itself is an energy store, and that force could increase or decrease the amount of energy in that store. We need an example. So here we have again the experiment with Rapunzel. Now, the important information that we need to know about Rapunzel in this setup is her weight. Now, before we found that her mass was 0.104 kilograms, which means that her weight is about 1 Newton. We also need to know how far she's pulled up from the ground floor to here, which is about 8.8 meters. That is how long this piece of string is, and that will be the same whether or not it is vertical or horizontal. So these two pieces of information are really important. Her weight, which is the force of gravity acting upon her mass, and also the height through which she's pulled. Let's have a little look at how much energy is transferred in that process. So we place her on the apparatus and we'll send her down. Here we go. $307 joules. Now this system we found before was only about 4% efficient. Now we're not going to rely on this at this stage. What we're going to do instead is we're going to keep this and just remember that this is very inefficient. Now here we have done work, in this case against gravity. But what happens if we change the force acting on her? Does it change the amount of work done? So now, rather than pull her against gravity, we're going to pull her against friction. Now there she is, right down there, and we're going to pull her horizontally across the floor. Now everything about this setup is exactly the same. It's the same system, the same efficiency, the same motor. So would you expect that the energy required to pull her, this same 8.8 meters, to be exactly the same as before? Will it be 307 joules? Well, there's only one way to find out. We must try it. $320 joules. It actually takes more energy to drag her across the floor than it does to lift her through the height of 8.8 meters. But what about a different surface? So here we go again. We've changed the surface of the floor. It is now a smoother surface. So is it going to take more or less energy than before? 320 joules was required to pull it through 8.8 meters. Let's have a look on this smooth surface. $293. It didn't require nearly so much energy to pull her on this surface. So what was different? Well, quite obviously, it was the friction, the force that was acting on her that she had to overcome to move across this surface was different, and that changed the amount of work that was done by this motor in dragging her along. But can we add more forces? Can we further increase this by adding more forces for her to overcome. So what about a parachute? Well, parachutes normally work by slowing the descent of somebody falling out of an aeroplane, like this. Now, what if we use that same parachute to add an additional force to Rapunzel as we pull her up? So as we pull her up, we're not only doing work against gravity, but we're also doing work against air resistance. The parachute should inflate behind. So here we go. If we're right, we should find that this takes more energy to pull her up, because we're working not only against gravity, but against air resistance. Now let's just check if we don't snag it. Let's see. And it works out at 334. It has increased the amount of energy that it takes to lift her up. That's very interesting. So what does this all mean? It's self-evident that if the string is half as long, then the amount of energy recorded on the joule meter will only be half as much. Going further, will in fact incur a greater energy transfer. More work will be done if Rapunzel is pulled for twice as far. But what do the other experiments show us? Is that there's something else that is very important, and that is the force against which you're acting. When Rapunzel was pulled vertically upwards, she was doing work against gravity in order to transfer the electrical energy of the motor through a mechanical energy transfer into the increase in the gravitational potential energy as she was lifted up. But the work was done against the force that was trying to stop it from happening, gravity. When Rapunzel was on the carpet, the force trying to stop her motion was friction. When she was on a more shiny floor surface, we found that there was a smaller amount of work done. This must have been because there was a smaller value of friction. When we tied a parachute to her, we were not only doing work against gravity, but we were doing work against air resistance. And so this meant that more energy was transferred in raising her through that distance. Now consider this. Work can be given by the product of two things. Two things seem to be important when calculating the amount of energy transferred. All of those systems showed that the distance through which the force was acting was important. Twice the distance, twice the amount of work done. So distance is an important thing in this formula. But what else? Well, I'll tell you what else. It is the amount of force. The force that has been overcome, multiplied by that distance, gives you the amount of energy that you've had to transfer to do the process. So in the case of Rapunzel being pulled up, she had to do work against gravity. So the force that was important here was the force of her weight. So the work done against gravity is equal to the force of gravity acting down on Rapunzel, which is her weight, multiplied by the distance through which she's been pulled. And what matters is the vertical distance, which we would call the height. And you should notice that these two equations are exactly the same. Work being equal to force times distance, and the work done against gravity being equal to weight times height. But what about those other situations we had? So work done against the friction of the carpet well, that would be equal to the force of friction multiplied by the distance over which she's experiencing that friction. Now notice in these cases we are naturally storing up work into, say, gravitational potential energy. What happens to something that is therefore then really high? It has all that energy naturally stored within it, and it will give it back again. It doesn't do work against gravity anymore, but what happens to the energy? Well, something dropped off a balcony will start to accelerate. It will overcome its natural resistance to changing its motion. And we call that resistance to changing its motion its inertia. Something dropped will try to overcome its inertia and will transfer all of the energy in its gravitational potential energy store into kinetic energy. And here is a further example. What about this? This device transfers energy from the batteries, the chemical energy, into kinetic energy. So what is work being done against? Well, it is being done against the inertia that Isaac Newton said with his first law of motion, that an object at rest stays at rest unless acted upon by a resultant force. Now this, with no resultant forces acting upon it, wants to stay at rest. However, what's going to happen is the transfer of the energy from the chemical to the kinetic means that work is done against inertia and the velocity increases.